Delaware Tech, Chemistry 100, Chemistry 110, Concentrations of Solutions. The concentration of a solution is a measure of the amount of solute dissolved in a total amount of solution or in the total amount of solvent, depending on which units of concentration we're using. So shown in this picture here, the blue particles are the solute and the pink particles are the solvent. So the more blue particles you have, the more concentrated the solution. The more solute is dissolved in the solvent, that is a concentrated solution. When you have less, we call it dilute. Please do not confuse concentrated and dilute with the words strong and weak. Strong and weak have totally different meanings in chemistry. So a lot of solute, concentrated, a little bit of solute, dilute. So we have many units to represent concentration. We can represent it in terms of the mass of the solute per volume of the solution or volume of the solvent, and those might be in grams per liter or milligrams per mil. Remember, a milliliter is the same thing as a cubic centimeter or a centimeter cubed, or cc. We can also use grams per milliliter. Grams per deciliter is a very common concentration unit used in clinical chemistry. It's being phased out a little bit, but it's been there for many, many years. And then one more unit of mass per volume is the percent mass to volume. And this is a measure of the mass divided by the volume of the solution turned into a percent. And we'll talk about that in another slide. We also have volume per volume units. So if you have a liquid solute dissolved in a liquid solvent, we would use units where both the units are volume, and typically we would use the same unit as representing the solute as we would for the solvent or the total solution. So we could use mils per mil or liters per liter or even percent volume to volume. So that's a volume to volume that's turned into a percent. And then one more unit that's very important to chemists, probably the most important, is the molar unit. And this is a unit that is the number of moles of solute divided by the liters of solution. And be careful about these. So moles per liter of solution is called molar, and the term for that kind of concentration is called molarity. We'll get to that in another slide as well. The abbreviation for molar is M, so whenever you see M, think moles per liter. Now remember, since chemical reactions don't happen in grams, they don't happen in mils, they don't happen in liters, chemical reactions happen in moles. They happen in the number of particles interacting with a number of particles. And this is why chemists strongly prefer to use the molar unit of concentration, moles of solute per liter of solution. So let's look at some of these concentration units. Let's look at percent volume to volume first, abbreviated percent V/V. And just to remind you, the word percent actually comes from two Latin words, per centum, which literally mean divide by 100 or per 100. So when you see percent, you have to divide by 100, but to create the percent, you need to multiply by 100. So just to remind you how percent is used in everyday life, 100% literally means 100 divided by 100, or 1. And 25% would be 25 divided by 100, or 0.25. Now, when we're creating a percent by volume, the name of the unit literally tells you the formula, percent V/V. So you're going to take the volume of the solute divided by the volume of the total solution. And a lot of people forget that it's the total solution. So the solute will be included in the denominator as well as in the numerator. So be careful when you're adding these up. And then you multiply by 100%. Remember, 100% is the same thing as 1, so we're not changing the number. We're just turning it into a percent by multiplying it by 100%. And then we get our percent by volume, or percent volume to volume. So here's an example. What is the percent of volume to volume, or percent volume to volume, of a solution if 25 milliliters of methanol, CH3OH, is diluted to 150 mils with water. Now, you have to be careful with the prepositions in chemistry word problems. Diluted to. Diluted to does not mean the same thing as diluted with or diluted in. So be very careful. So when you say diluted to, that means the final volume is 150 mils, and you got that by adding whatever water you needed to add to get to 150 mils. So that's telling you 150 mils is the total volume, not the volume of water, just the volume, it's everything. It's the water and the methanol together. Whereas the methanol alone is the 25 mils that's stated in the beginning of the problem. So you're going to divide 25 mils by 150 mils, that's your total, and then turn it into a percent by multiplying it by 100%, and you get 16.666 repeating percent. Of course, you'll notice in the problem, 25 mils and 150 mils both have only two significant figures, so we need to round to our answer to two sig figs to give us 17% volume to volume solution, and that's how we would write the unit percent volume to volume or volume slash volume. Percent by mass is slightly different. So instead of dividing the volume of the solute by the total solution volume, we divide the mass of the solute by the total solution volume. And in this case, we need to know the total solution volume. If we're adding only a little bit of solute to the solvent, it's not going to change the volume that much. But if we had an enormous amount of solute, we might need to know what the total solution volume is. So this is a more common unit than the volume to volume because usually you have solids dissolved in liquids as more common solutions than liquids dissolved in liquids in the laboratory. This unit can also be used for liquids to liquids as well. So it's more common unit. So here's an example. 4.8 grams of sodium chloride are dissolved in 82 mils of solution. So you were given the total solution volume of 82 mils. You're given the number of grams of solute. You merely divide the grams by the mils and then turn it into a percent. So we'll multiply it out. We get 5.854%, which we need to round to two significant digits again to give us 5.9% mass to volume. Another problem might give you different parts of this equation shown at the top. How many grams of salt are there in 52 milliliters of a 6.3% mass to volume solution? So now you are given the actual concentration, 6.3% mass to volume. And you can think of this as meaning 6.3 grams per 100 mils of solution. That's one way to think about it. And you could use that directly, or you could plug the numbers directly into the formula shown at the top. We know the concentration percent by mass is 6.3% mass to volume. We know the volume of the solution is 52 mils, and then we stick those numbers in, and we also have that times 100%. And now we're going to solve for x, so we need to rearrange our equation. So the 100% will go to the bottom of the left side of the equation, and the 52 mils will go to the top, the numerator of the equation. And that merely gives us 63% times 52 milliliters divided by 100%. Well, remember, 6.3% divided by 100% is just 0.063 with no units at all, because the units percent cancel with percent. And that leaves us with an answer when we multiply times 52 mils of 3.276 grams of our salt. And of course, again, we have a problem where the two numbers we were given have two significant digits, so we round to 3.3 grams of salt, and that is our answer. So the third unit of concentration that I want to talk about, and this is by far the most important to chemists, is molarity. And we express the unit as either moles per liter or a capital M. The capital M means moles per liter. molarity. Please don't use a little m, a lowercase m, that has a different meaning. That's for a different unit that we're not going to talk about in Chem 100, called molality, and that has a totally different definition. But molarity with a capital M is the moles of solute divided by the liters of solution. And if you see M, just automatically convert it to moles per liter in your head or on paper. So here's a question. What is the molarity of a solution with 2.0 moles of NaCl in 4.0 liters of solution? So you'll notice you were given the whole volume of the solution, not just of the water that it was made with. And you're given the number of moles of sodium chloride. Now, if you're not given how many moles of sodium chloride and you're given grams, you need to convert grams into moles first. And in order to do that, you need to first determine your molar mass of sodium chloride. But we already are given the moles of sodium chloride, so we just take the moles of sodium chloride and divide it by liters, and we get 0.50 molar, and you'll notice that has two significant digits like the two components of our problem, so that's our final answer. 0.50 molar sodium chloride is our concentration. So here's another problem. What is the molarity of a solution with 3.0 moles of KBr, that's potassium bromide, dissolved in 250 milliliters of solution? Well, remember, our volumes must always be in liters. So as soon as you see mils of solution, just automatically turn that into liters if you're going to be doing molar concentrations, molarity. When you're doing percentages, you want to use milliliters and you need to multiply by a percent. But when you're doing molarity, there is no percent, and everything, all the solution volumes must be in liters. So be careful not to confuse these. So we take 3.0 moles of KBr and divide it by 0.25 liters of solution, and we get a concentration of 12 molar potassium bromide. So how do we make solutions in the lab? Well, you might think, oh, you just take the solute and you put it in the solvent and you mix it up and you're done. But remember, we have to be careful about having the exact right solution, and we don't always know how much solvent to add. Because remember, the solute can take up volume in our container as well, and we don't always know what that volume is. Sometimes that volume is 0. Oddly enough, sometimes that volume is negative because the solution volume is less than the sum of the volumes of the solute and the solvent. And that is because of the tight interactions between solute and solvent. So we really need to know exactly what our total solution is, of course, but we don't always know how much solvent we need to make it. So what we do first is only put in part of our solvent, maybe half, maybe 2/3. You use your own judgment when you're making it. And then you weigh out your solute, and you need to calculate how many grams you'll need. Okay, if you're depending on what kind of unit you're going to use for concentration. If it's molar, you need to calculate how many grams you need based on how many moles you're going to need. So first you do that calculation, and then you weigh out on the balance, or mass out on the balance, the exact amount you need of the solute. At this point, you're going to add the solute and mix it to your solvent. And once you get it mixed, and that might take a lot of stirring, it might take warming up, it might take just shaking with your hand, mixing it. But once you get it dissolved, only then can you bring it up to your final volume. And some of these containers, like the volumetric flash shown in this diagram, have a line on them that tell you exactly where a certain volume is. So you need to be very careful adding the last bit of solvent drop by drop so that the bottom of the meniscus of the solvent reaches that line. And then once you've reached that, you make sure you mix it very well again, so it's much easier to mix your concentrated solution with the excess solvent that you're adding, the extra solvent you're adding. It's much easier to do that than to bring up your volume right to the top and add solute and hope that you don't overflow your line. So this is why we only put a little bit in at a time. So our concentration, especially when we're dealing with molar concentration, is going to be equal to the amount of material we have, and in this case it'll be in moles, divided by the liters of solution. So concentration is equal to our moles, our N, our number of moles, which we abbreviate N, divided by our volume, which will be in liters. And you can express that in terms of units as molar, the capital M, equals moles per liter. And you can rearrange that equation to see that the volume in liters times the concentration in molar is equal to the number of moles. And if we if we keep that same equation, but instead of using the units, we use the actual properties, volume times concentration is the amount in moles. V times C equals N. And this will come in handy when you're doing a lot of other calculations later. So remember, V times C is your N, or volume times concentration is your number of moles, which means your volume in liters times your concentration in molar. Remember, molar is moles per liter, so liters cancel, and you're just simply left with moles. So, how many moles of sodium chloride are needed to prepare 6.0 liters of a 0.75 molar solution of sodium chloride? Well, we know the volume, and we know the concentration, but we know that multiplying the volume times the concentration, and you'll notice I turned molar into moles per liter. More specifically, I turned it into moles per 1 liter. And in fact, you can think of concentration as a conversion factor. 0.75 moles of sodium chloride is the same thing in this case as having 1 liter of solution of sodium chloride. So that's a conversion factor. The numerator equals the denominator. They are equivalent quantities. And therefore, when I multiply it by 6.0 liters, I can get the number of moles that's equivalent to 6.0 liters, which in this case is 4.5 moles of sodium chloride. The liters will cancel in this case. Here's another problem. How many grams of calcium chloride are needed to prepare 625 milliliters of a 2.0 molar solution? Well, remember what molar is. It's moles per liter. And we have our volume in milliliters, and we're asked for grams. So these things don't really match up. Molar is moles per liter, but we don't have moles. We're asked for grams, and we don't have liters. We're given milliliters. So you have to do a couple things first. First, you have to determine how many moles you actually need. But before you even do that, you need to determine how many liters you are making. Well, it turns out 625 milliliters. Just move the decimal place 3 times, and you realize that 625 milliliters is equal to 0.65 liters. So that's your volume. Remember, volume times concentration is moles. So we multiply it times our concentration. Our concentration is 2.0 molar, or 2.0 moles per 1 liter, because we have 2.0 moles of calcium chloride in 1 liter of solution of calcium chloride. So that's our conversion factor to convert liters to moles. We now know we need 1.25 moles of calcium chloride. Now, you'll notice I did not round this number. It is important not to round until you get to the final answer of any problem. So be careful about rounding. You get what's called rounding error if you round too early. Then we need to turn our moles into grams. So we know how many moles of calcium chloride we need. How do we turn it into grams? Well, first we need to know how many grams are in a mole, and that number is the molar mass of calcium chloride. And we get that by adding the molar mass of calcium, which is the same as the atomic mass with the units grams per mole. Calcium has a molar mass of 40.078 grams for every mole of calcium, and chlorine has a molar mass of 35.453 grams for every mole of chlorine atoms. And we multiply that by 2 because we have 2 chlorine atoms in a calcium chloride formula unit, CaCl2. So when you add those together, you get a total molar mass of calcium chloride of 110.984 grams per mole. And there's no need to round this number because we have the right number of decimal places anyway. We can go out to the thousandth of a gram per mole here because of the numbers we started with. So now we have our molar mass. We have a way of converting moles into grams. That molar mass is our new conversion factor. Anytime you have a unit that has something divided by something in the unit, that value is automatically a conversion factor that will allow you to convert from the top unit to the bottom unit or the bottom unit to the top unit. So grams per mole, if I know the grams per mole, I can turn grams into moles, I can turn moles into grams, depending on how I write this. And how I'm going to write this would be using it as the number of moles, the number of moles per, the number of grams per 1 mole in our equation. So we're going to take our 1.25 moles of calcium chloride and multiply it by our molar mass in this format, 110.984 grams per 1 mole of calcium chloride. It's that many grams of calcium chloride per 1 mole of calcium chloride. So again, anytime you see a molar mass, rewrite it as that number of grams of that substance divided by 1 mole of that substance. And you have your conversion factor. We multiply it by our original number of moles. We get 138.73 grams of calcium chloride, which we can finally round to 2 significant digits, to 140 grams of calcium chloride. So when we're preparing our initial solutions, remember we have to keep track of how many moles we have and how many liters we have if we're doing it in molar concentration. So automatically, when you see grams, turn it into moles. When you see mils, turn it into liters. When you see molar, turn it into moles per liter. And this will help you do your conversions much, much quicker. So here's the problem. 10.3 grams of sodium chloride. Okay, you see grams. You're probably going to have to turn it into moles, and that's going to require finding out the molar mass first. This many grams are dissolved in a small amount of water, then diluted to a final volume of 250 mils. Okay, is it important to the calculation that it was dissolved in a small amount of water first? No, but it's there because that's how you have to do it in practice. The final volume is what you're concerned with, 250 mils, and we already know that first we need to turn that into liters, and we know that that is 0.25 liters of solution. So what do we need to do first? We need to calculate the molar mass of sodium chloride. The molar mass of sodium, 22.98977 grams per mole. The molar mass of chlorine, we already stated, 35.453 grams per mole, and you get a total of 58.443 grams per mole. Now you notice I did round that because we can only trust up to the thousandth of a gram per mole for our molar mass, and this is a well-known number in any case. So we're going to use this to convert our grams of sodium chloride to moles of sodium chloride. So in this case, we're dividing by our molar mass. We're putting the 58.443 grams of sodium chloride on the bottom in the denominator and our 1 mole in the numerator. It's always going to be versus 1 mole. So when you multiply that out, or divide if you're using the calculator, obviously, you'll get 0.17624 moles of sodium chloride. Far more significant digits than we're supposed to have, but we're not done yet. And we know our volume. We convert our 250 mils to 0.25 liters. If you're not used to doing that directly by looking at the value, you can always convert it using 1 liter divided by 1,000 milliliters. That's your conversion factor to get 0.25 liters of solution. So now we know the number of moles, we know the number of liters, we divide the moles by the liters, and we get 0.70496 molar, or moles per liter, which we round to 0.70 molar sodium chloride. How many grams of glucose, whose formula is C6H12O6, are needed to make 125 mils? Okay, so you're already been asked for grams, so you should be thinking moles first, and you're given milliliters, so you should be turning that into liters right away, of a 0.50 molar solution. Instantly, you should think 0.50 moles per liter. So you see grams, you need moles first. You see milliliters, turn it into liters. You see molar, turn it into moles per liter. And this will make it easier. Now I've given you the molar mass of glucose so if you add the molar mass of 6 carbons plus 12 hydrogens plus 6 oxygens, you'll get 180.1559 grams per mole, or that many grams per 1 mole of glucose. So first we need to figure out how many moles of glucose we need. Well, we have a volume, and we know it in liters, 0.125 liters. And we know our concentration, 0.50 moles per 1 liter, or moles per liter. The liters will cancel, and we'll be left with 0.0625 moles of glucose. Well, now we have our moles of glucose. Now it's a matter of converting moles into grams. We multiply it by the molar mass, which is grams per mole. Moles will cancel, and we'll be left with 11.2597 grams of glucose. Since our concentration only has 2 significant digits, 0.50 molar, we have to round our answer to 2 significant digits, or 11 grams of glucose. And with that, we'll stop here.